All right, so let's take a look at a wave propagation and look at a way to conceptualize it that was kind of created by Christian Huygens. Right? So a way of looking at wave propagation is we have this source, and it oscillates up and down, like maybe you threw a rock in a pond, right? And that caused the water to go up and down, and that disturbance then starts to propagate outwards in a big circle. Right? On a pond surface, this would be a 2D circle, and if it were a sound wave or an oscillating electron that caused electromagnetic radiation, it would go out in a 3D circle, which is a sphere, right, or a spherical shell. Right? So a moment later, if we wait for that peak to travel further out, right, then one period later, that peak will be here. Next period later, it'll be here. Right? Next period later, it'll be here. Right? And of course, the energy is dissipating, as we know, by 4 pi over, by the initial power over the 4 pi r. Right? That intensity is dropping off because it's spreading over a larger and larger area. Right? And this is what happens when you make ripples in a pond. Right? They spread out into these peaks, travel out in these kind of regular waves. Okay, so we get these waves coming out like this. And what Huygens realized, this neat little trick, was that every point on that wave front, any of these wave fronts, can then be treated conceptually as a new wave source, right? A source of these new, what we call spherical wavelets, right? And so we think of this as being built up of a bunch of little sources, like little tiny pebbles being dropped into the water here, right? And then each one of these then ripples outward as if they were a source on their own, right? But they all start in phase, because these were all at a peak of a wave, right? And so we replace the wavefront with a bunch of little oscillators, but all at the peak. And then we let them go. And they're all going to oscillate at the same frequency as the source that created them. Right? So then they propagate outward and outward, right? Each one of these is a circle centered on that new wavelet source. Right? But then, the neat thing here is if you then look and see what do these series of wavelets add up to be, right? They're not individual wavelets. There were all these little wavelet sources, and they're all going at the same time. So if I want to know what I'm going to see further out, I have to superimpose or use superposition to add up all these wavelets. And so that's this line right here. If I look at where all the peaks are, right, it's right here, and that ends up being exactly centered on the original source. Right? If I instead had not done the wavelet trick and I had just kind of kept going, made another circle that was wider, another circle that was wider, right? Just done this, 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 I would have eventually ended up with a circle out here. Right. So that seems like a lot of trouble, right? To generate something that's an obvious statement, right? That the waves will eventually get out here if I just had kept going. But it's important because when we start to not have things that break up this interface, right? If I don't let all of them through and let only these 3 get through, basically sending a wave through a barrier. And when that barrier could be a barrier in, like a reef break, or it could be your pupil, right? Because light's coming out in these big waves, but only a small portion of those waves make it in through the iris of your eye and onto your retina, right? So we need to know how things pass barriers, right? And this becomes, as I'll show you all, hopefully, maybe, let's see. I think I have a couple more slides I want to get through, right? You'll see how this will be affected when you hit a barrier. So this wavefront, so we call each one of these things a wavefront, right? So each one of these was considered a wavefront, and we can build up additional wavefronts or future wavefronts by taking any wavefront, treating it as a bunch of coherent sources, and then doing wavelet addition from there, right? The wavefront is defined as the line, or in this case the curve, that connects all the points of constant phase, where all of these things were at their first peak, right? Or at their second peak. If I think pushing water up and down, I connect where all the peaks are of that wave, that's my wavefront, right? And right now it's going to be a curved circle, right? But sometimes we might do something that actually puts a dimple in it. And what we do is in optics, that would be a lens. A lens turns out to take some of those waves and slow portions of it down so that you end up with some of the peaks further back. And then if you draw the wavefront, it comes with a little dimple. And we'll work on that when we get to the geometric optics. But one last thing I want to show you really quick is the idea of this infinite plane wave. If we take, instead of a single source and let it go out, if I start with something that's already a pushed plane wave, a straight plane wave like this, right? If I start going Huygens wavelets from here, right, it will then, and I draw the tangent to all these guys, it'll create another plane wave. Right, so the other thing that we have is an infinite plane wave that if we start with an infinite plane wave and do Huygens principle, it will create another plane wave. So those are self-propagating. Right, so the last question is, how do I get an infinite plane wave? Well, I just go out far enough from any source. Right, so this is a round source, it's sending out waves like this. Right, but by the time they get to the Earth, that curvature is pretty darn small. Right, if I zoom into San Diego, that curvature is practically non-existent. So even though the star is actually, if you get nearby the star, you'd say, oh, it's making spheres of waves. By the time I get to, light years away, right, those waves are effectively planar. And the same can be said for a small light bulb many, many meters away, right? And in a large enough approximation, that's a planar wave. Right? Same thing for light from the sun, because we are many sun diameters away from the sun. Right? For a light bulb, if I just go far enough across the room, I am many light bulb diameters away. We can also treat that as a plane wave. All right. So why is this not overkill? It's not overkill because inherently what I've done, kind of implicitly what I've done, is when I've drawn these figures, I've drawn this bunch of dots, but I'm kind of assuming that these dots keep going, right? That these lines are infinite, truly infinite plane waves, and there's another dot here, another dot here, another dot here, and more down here that I haven't drawn, right? In which case, right, there would be if I summed all these, I would draw a line here, and I would just keep going because there's another dot here that makes another orange circle out here. There's another dot here that makes another orange circle, right? But what if I break that assumption? What if I say, I no longer have an infinite plane wave like this that just goes on and on, but I'm going to block part of that plane wave, right? I'm going to have light coming in from the sun, and I'm going to make it go through an opening, a finite opening, right? This could be water from the ocean, waves from the ocean going through like a break in the barrier reef, or whatever, right? How do we deal with this, right? What will the wavefronts look like on the other side, right? And there's two ways that you could imagine this intuitively, right? Or at least kind of guess at. One would be they'll still be straight lines and they'll just be chopped off, right? But that turns out not to be what happens, or at least not exact. It's not exactly right. To be exact, you have to take into account diffraction. And when you pass an infinite plane wave past a barrier, for example, a hole, we break I shouldn't maybe not say symmetry, but I break the uniformity of that infinite plane wave. It's no longer just bright everywhere. It's only bright in certain places. And so we end up with Huygens wavelets near the edges that aren't matched by other things further down. Right? So here, I only have these number of dots to create wavelets. Right? It looks like the same thing I drew before. Right? You could just say, oh, that's an infinite plane wave. Right? But now this thing doesn't have another dot over here to go like this, to kind of prop it up. So if I really were to draw the tangent to these lines, and these are the only ones that are there, and maybe some in between, then this is the last one. So I have to do this, right? And as a result, if you believe Huygens, and it's true, then at the edge of a barrier, at the edge of an opening, you get a bending of the wavefront, and that's what we call diffraction. When they pass through small openings. So how small is small? Right? Well, it depends on what kind of wave you're passing through. Right? It turns out there's not one size where diffraction happens, and that's it. So it's relative. Relative to what? Right? If you had to guess, what's the most important length scale when we're dealing with waves? The wavelength is pretty much the only one we have, right? The only really important one, only important thing that sets any sort of scale, any length scale, when we're dealing with waves is the wavelength. So small, you could reasonably guess, is small compared to the wavelength, and you'd be right. Okay? So as long as the opening is on the order of a wavelength or small compared to it, then you will get substantial diffraction. You'll always get diffraction, right? It's just that the angle of diffraction will be so small if the opening is very big that you may not really notice it. So let me show you that. Right? If you pass waves of this wavelength, you can see the wavelength between these two waves, through an opening that's very big compared to that separation between the wave peaks, right? Then you do get a little bit of bending here, right? But not a lot. Right? As they pass through the barrier, it exhibits diffraction. But as the size of the hole decreases compared to the wavelength, the wave that passes the barrier goes from being nearly planar, right, to being much more spherical. And by the time you've closed it down to this, you pretty much got a little point source here, so it makes sense that the waves going out would look like the waves coming from a point source, more spherical. Right, so the angle of diffraction, which I can highlight for you here, is small when the opening is big compared to the wavelength. And the angle of diffraction is large when the opening is small compared to the wavelength. Right, and to understand the power of this, we can take something as esoteric as the equation for a diffraction grating, or for diffraction in general, and pretty much just from this logic, just from like having drawn these little tiny circles going out, derive something very close to the correct form for that, conceptually derive the form for that equation. Right? We basically said that the angle that it's going to diffract at, right, is going to depend to some degree on how big the opening is, but not just how big it is compared to the wavelength, right? If it's big compared, so we're looking at a ratio of the size of the opening to the wavelength as the relevant thing, right? Is it going to be just proportional to this? Well, we said when the hole gets small, right, then the angle gets big, right? We just worked that out mentally, right? So if this ratio of how big my opening is compared to my wavelength gets small and this gets big, then it must be 1 over, right? So something like that. Okay, but 1 over this is just lambda over d, right? So we've already basically got something along the lines of lambda kind of goes as d and a theta. It turns out that this is a d sine theta, and we'll have to work out the math to get it just right. It turns out it doesn't go linearly as theta, but it goes as the sine of theta. But look how close we got. Look how we got to the functional form, and we just had to remember, we'll have to go through the math to show you, and I will, why it's a sine. But if you ever forget stuff like this, just a good mental picture will get you 90% of the way back to where you need to be. Okay, so let's open with a clicker, or let's start with a clicker early on. I'm trying my best to get these things in earlier. Okay, so from far away, we'll combine a few things that we've looked at in the last couple lectures. From far away, I shine a green light beam onto a black piece of cardboard so that it illuminates a 5 micron wide slit, right, 5 micrometer wide slit. The slit is placed on the other a screen is placed on the other side, and it shows that the beam has diffracted slightly. Right, so as the light waves went through this small opening, it diffracted a little bit. What can I do to make the beam diffract more, right, to larger angles? Right, can I change it to a red light, from green to red, from green to blue, make the slit wider, make the green light brighter, or will none of these work? Okay, so let's go ahead and argue with your neighbors. Five, 4, work under pressure, 3, 2, 1, last call. All right, let's see how we did. All right, we have a reasonable majority saying A, change it to red light. Some people are saying change it to blue light. Making the slit wide, let's look at the ones that didn't work, right? That very few people voted for. Right, making the light brighter, that's just going to make the whole pattern brighter, right? So that's not going to help. There's nothing in what we've said about how intense the light is will make it diffract more or less, right? Making the slit wider, let's see what that would do, right? We said if we have a particular wavelength and we make the slit wider, right? What mattered was how the smaller the hole was, the more it would diffract, right? And so making it wider would make it diffract less. So that's going in the wrong. It has an effect, but it's going in the wrong direction of what I asked for. Right? So then let's look at blue light. Right? Blue light is over here on the, you can look at this as short wavelength end, right? So if it's a short wavelength, right? If I'm a smaller entity trying to get through the same size door, I'm now going to see a bigger door, right? a tall person, a smaller wavelength, right, which is what blue is, right? A shorter person will try and walk through a particular doorway and say, oh, this doorway is huge. I got plenty of room. No need to diffract, right? But a very tall person, something with a very long wavelength trying to walk through the same size door will go, whoa, right? So there's a small opening, and small openings relative to the size of the wave cause more diffraction. Right? So it looks like red light is the correct answer. Let's see if I agreed last night. Yes, I did. Okay. So now that we understand something about light waves and how they propagate, let's start looking at how they might interfere with each other, right? So in order to create a sustained and stable interference, right, and we can go through this a little quickly because we already kind of talked about this with sound waves interfering, right? You need at least two sources. They have to have the same wavelength in order to have a stable interference. Remember what happened when we had two different wavelengths, right? We got beats, so it wasn't stable, right? Over time, it was changing in amplitude, right? We got woo, woo, woo. If I want something that's just stable, so the pattern where it's dark, it stays dark. Where it's bright, it stays bright. Then I need to have them at the same frequency, so that means that they have the same wavelength, and it means that they have to be coherent. This is a bit of a new word for us, at least it is in the scientific sense, right? What do we mean by two sources being coherent? There's actually two different types of coherence. One is kind of sometimes implied, and that's the temporal coherence, right? What we're talking about here is spatial coherence. But let me take a moment to kind of distinguish those two, just so you know it, because if any of you start to use kind of more fancy microscopes, you do have to know the distinguish between the two. So spatial coherence. Coherence is just talking about things being in phase and staying in phase, right? So if something is up at its peak, the other one is up at its peak. Or, and if something's down at a trough, then the other one is predictably down at the trough, right? Some sort of predictability between waves. Right? Spatial coherence is like two people standing on the beach, right? So if I stand next to a friend on the beach, right, and I ask my friend to close their eyes and to trust me, right, and they look at me like, I'm not gonna trust you, but never. So, and I asked them, close your eyes, and when I say the water coming, I'm gonna tell you to jump, right? And let's assume this person actually trusts me, and so I say, okay, ready, jump, and they jump, and then they will miss the wave, right? Then we take a step apart, right? So now they're a few feet away from me, right? And we do the same thing. When I see a wave coming to my feet, I say, jump, and then they jump. This will continue to work for a while, right? But you know that if I get all the way up to Solana Beach, right, while they're down in PB, and I say, jump, right, first of all, ignoring the speed of sound, right, that the waves hitting the beach are no longer in sync, right, they'll break apart, right? So spatial coherence is how far laterally I can move before waves start to decohere, right, go out of sync. Temporal coherence would be if I stood in one spot by myself and I time the waves, right, and I see, okay, I have to jump, and then I have to jump, and I have to jump, and I'm like, okay, I see what's going on here. So then I close my eyes and I get cocky, and I go, okay, I have to jump. Oh, look, this is easy, right? And this might work again for a while, but then over time, the frequency might shift. There might be a break in the waves, right? They aren't completely regular, right? So for a purely sinusoidal wave, it'll work forever, right? But nothing is purely sinusoidal forever and ever and ever, right? So real sources will break, there'll be a sine wave, and then for some reason or other, it will break. And then it may continue to be a sine wave, but maybe it's jumped from being the peak to the trough, right? That's not gonna happen so much in our class. We're just gonna assume perfect sine waves, but that's what people mean by temporal coherence, right? Okay, so we're gonna assume for most of these problems that we work with that we have temporal coherence, so these, this peak to this peak to this peak is very predictable, right? And also that when this one's at a peak, this one's emitting a peak, this one's emitting a peak. That's spatial coherence. And to make life easy, we're also going to pretend, this is referring to an old chapter, so forget this, chapter 24. We're only going to look at the case where we have a single wavelength, right? Unless we explicitly say there's 3 wavelengths of light coming in, or we use white light, right? So that means that we have a single pure frequency and a single pure wavelength, right? 632.47 nanometers for red laser. Any questions on the idea of coherence? Okay. This is just kind of a prerequisite to being able to do interference problems. It was the same thing for sound waves as well. Those sound waves had to be coherent over space and time. Okay, really quick question. Let's just do this. This will help me get a sense of how many people are on board and how many are maybe needing to review a little bit. All right, so in order to get complete cancellation between two coherent waves, the path length difference for the two waves can be which of these? Yeah. All right, let's close it down. 5, 4, 3, 2, 1. And let's take a look. All right, so most of you got it right. Those of you who I can understand why you would pick a full wavelength, but let's be careful. Full wavelength would be for constructive interference, right? Not for cancellation implies destructive, right? You want the peak of one to be at the trough of the other. And if they are coherent, meaning that they are spatially coherent, so they are both emitting a peak at the same time. If one has traveled 5 wavelengths and the other travels 6 wavelengths, they're both still at the peak, right? So they won't cancel. It's a +1 and a +1. But if one travels 5 wavelengths and another one travels 5.5 or 4.5, right, then one's at a peak when the other's at a trough, right? That's a very fundamental, you have to understand this in order to do any of the homework problems or any of the quiz problems. So make sure if you got this wrong, it's time to go back and review. Okay. Okay, so half a wavelength. All right, so now we're going to take a look at what will happen if I take these two waves. I showed them for water waves or sound waves. We're going to do the same thing, right? And this will make, I think, having talked about it in terms of sound waves will make this a lot easier this time around. I think we've held off on looking at interference before with sound. So this is almost review. It's just now instead of sound waves, we're doing light waves, right? And instead of strong, bright, loud sound or soft or no sound, we're looking at bright light regions and dim regions of very little light. Right, so we're going to take a screen and we're going to poke 2 holes in it. Okay. And because the waves emerging from the right of the 2 slits, right? Let's call this one the one on the right and this one the one on the left. If you were standing over this way looking at it, are in phase because we shine light on it from some sort of coherent wave source, right? It could be the sun, right, which is generating plane waves. And then these are both peaking at the same time, so that lets through a peak here and that lets through a peak at the same time. If the screen is placed to the right over here, then what you're going to see is a pattern of bright and dark bands. We already saw this with the 2 speakers. We had regions of high intensity, low intensity, high intensity, low intensity, or low amplitude, right? Okay, and this is called Thomas Young's double slit experiment. He first did it over 100 years ago. So let's analyze this, and by the time we're done analyzing this, we'll understand where this sign comes from, and then you'll have basically derived the diffraction equation, okay? So let's define a point Q midway between these 2 slits, between these 2 openings, and a point O, which we'll call where the central maximum on the screen is. Right? So if we go back here, where the center maximum bright light is, right? We have red light coming in, and we have a big bright red band right here at this point on the screen, which is obviously by symmetry, you can imagine that's going to be right in front of the 2 holes, right? Symmetrically in front of the 2 holes. We'll call that O. And the center maximum, at the center of the center maximum on the screen, right? So then we'll define an angle here, theta, that is the angle from the center line up to the first, whatever fringe we're looking at. So we're going to look for where do we have a bright fringe. So we start with a bright fringe in the middle, where we're going to have a dark band, and then where we're going to have our first bright fringe, and then the second dark band, and the second bright fringe. Okay. We'll label the distance between the slits as being d, right? That's our distance between the slits. And the central, my fingers keep clicking the wrong thing. The central maximum fringe has an angle of 0, right? If I ask you what's the angle to any particular point, I start naming things off, first bright fringe, second bright fringe. If I just say, what's the angle to the central maximum? Well, by definition, that's 0 because we defined our angle from that line that connects to the central maximum. The path length difference between the two waves to any point, we're going to call delta, right? So that's just the difference between how far the light had to travel from slit 1 to the point of interest versus from slit 2 to the point of interest. We labeled this one as R1, we labeled this one as R2, and we notice that the distance that R2 is bigger than R1, as I've shown in this picture for this point, right, by this much. That's what we'll call delta. Sorry, I'll go back and pause. Any questions on just the basic nomenclature? Right, and hopefully you can see that if I had picked the point to evaluate as the central bright fringe at O, then the delta would be 0, right? Because R1 and R2 would look symmetric, and they would have a difference of 0. All right, so in the center of the screens, both waves have traveled the same distance, as I just said, and so they'll arrive in phase because they're leaving in phase. But at the center of the first off-center fringe, the wave from the lower slit has traveled exactly 1 extra wavelength compared to the light coming from the top slit, or the left slit, however you want to call it. But if they've traveled 1 whole wavelength apart, then they both arrive at their peaks at the same time. They both arrive at their troughs at the same time, right? So if I had a detector that was very, 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 very fast, right, and I could see these oscillations, it would still oscillate, right? It'd still be oscillating. Both peaks would come, both zeros would come, both minus ones would come, right? And it would add up to +2, 0 to -2. But this is going at a frequency of like 10 to the 14 hertz, right, for light waves, right? We saw that on the spectrum. That's faster than any detector known to man, right? So we never really see these oscillations. What we see is the amplitude squared intensity, right? And so we see this as a bright spot. Whereas in sound, we would have said, oh, it's a high amplitude sound wave because of high amplitude oscillation. Same thing here, but we're going to look at the intensity, which is that amplitude squared, and we just say that's a large bright spot. Okay, so they are both arriving in phase, but now it's off by 1 wavelength. And you can see why I wanted to mention the temporal coherence, right? Because if I start to walk off more and more to the second bright fringe and the third bright fringe, then I'd be off by 1 wavelength and 2 wavelengths and 3 wavelengths, right? If my source kept breaking, right? If I go, like, I'll go 1 cycle and 2 cycles for a nice sine wave, but then all of a sudden I jump, right, in some weird way, then I'm trying to line up this first wavelength, or first peak from this one with the 5th peak of this one, and if in between those things something had happened, then you can't say for sure that they're going to both peak at the same time anymore, right? So you do need both temporal and spatial coherence. A lot of times we just kind of implied the temporal coherence. Okay, so between those 2 bright fringes, there's going to be a point where, if this thing is both, they're off by 0 wavelength, and this is off by 1 wavelength, there's going to be a point in here where it's off by half a wavelength. And we just saw from the clicker question that if you're off by half a wavelength, and the peak of one is at the trough of the other, so when this one's +1, this one's -1, cancels to 0. When this one's at 0.25, this one's at -0.25, cancels to 0. 2 zeros cancels to 0, right? So there the oscillation amplitude goes to 0, and that means that the total amount of light we see is nothing. Okay, so we end up with a dark fringe. Right, so now let's do this and see if we can figure out where that sign comes from. Okay, so we have all these things we defined. L is the distance to the viewing screen. P is the point that we're going to evaluate. D, again, is the separation between the slits. We're looking at this angle, theta. Right? And we have the 2 path lengths, R1, R2, and the difference between the 2 path lengths is this delta. Now, the problem is that on a finite PowerPoint slide, I cannot draw a Young's double slit experiment accurately. Right? Either the 2 slits I'm going to have to draw so small, the distance between them so small that you couldn't even see that there's two slits, or I'd have to put the screen over in Urey Hall, right? The view screen here, this point O, right? That's the reality of it. Like if the opening between these slits are usually very, very small, and the screen would be over here, right? So we've blown it up, but in blowing up only one axis, this no longer is a very good representation, because you look at these two, these don't actually look parallel to each other, right? But in the limit that if I made the screen very, very far away, right? If I go further back, further back, further back, eventually they'll get to being almost parallel, right? And so we're going to work in that almost parallel limit. We're going to call, and say if I push the screen far enough back compared to the separation between these, this is only going to be like a couple for light, it's only a couple microns, right? So even a meter back is 1,000,000 times bigger, right? This is clearly not 1,000,000 times bigger than this. So let's take it to the point where this thing is 1,000,000 times bigger than this, and then these two are practically parallel. If those are practically parallel, then this forms a right triangle. Right? These are two parallel lines. If I draw the perpendicular to this, right, then these two are now the same length, right, because they're going to the same point very, very far away. And the difference between them is just this little portion right here. Okay? Now notice I labeled this angle and this angle both with the same symbol theta. Right? That's because it turns out they are the same angle. Right? And we did this in 1A, right, when we took an inclined plane and then we drew, right, the y component of gravity and stuff. But let's do it one more time just to take a look. Right? How are these two angles, which are these two angles, the same? Well, if this is truly now parallel rays, or nearly parallel rays, this is a right triangle. Triangle sums to 180 degrees. That's a right angle right there, so that's 90 of the 180. So these two have to add up to 90. Right? So this is 90 minus theta. But this is a right angle too. Right? So if this is 90 minus theta, then that has to be theta again. Right? So these two angles are equal. So what we're interested in, you think about, is this angle. We're trying to figure out how far what angle do I have to look at before I see that first bright fringe or the second dark fringe, right? But to do the trigonometry, it's easier to look at this angle, which we now see is the same. All right, so let's look at this angle. If I look at this angle, we agree that, well, I told you, and nobody objected, that this is delta. This is the difference between the path lengths from slit 1 and slit 2 to that point of interest, right? This is a right triangle. We're trying to get that angle, and I know the hypotenuse of this right triangle, it is d, right? The separation between the slits. So d, let me put it this way. If I take the sine of the angle, it would be the opposite over the hypotenuse. So sine of theta is delta over d. Right, so rearranging, delta is d sine theta. And maximum constructive interference, when the two peaks perfectly line up, is going to occur when those path length differences are a full wavelength apart, or 2 wavelengths apart, or 3 wavelengths apart, right? Or m integer wavelengths apart. So that means delta has to equal to m lambda. But we just agreed that delta is d sine theta. So m lambda equals d sine theta, and that's your diffraction equation, which is very close to what we intuited. We just didn't have the sign, right? And we also weren't looking to look at the second order and third orders. Yeah, Chris? Delta is the physical distance from slit number 1 to the point that I'm looking at compared to slit number 2 to the point I'm looking at. If this, like, let's say the point I'm looking at is, let's say the center of this orange chair is right between these two guys, right, on the screen. To you is the left corner of that chair is off center. The distance from here to there might be 3.1 meters, and the distance from here to here, because it's now at an angle, might be 3.12 meters, right? That extra 0.02 meters is delta. Okay, that's the physical distance. The question is, that 0.02 meters, for the wavelength I'm using, how many wavelengths is it, right? And we're saying that if it's going to be a bright spot right at that point, then that delta, that physical difference in path length has to equal to an integer number of wavelengths, so that you end up with a peak and a peak again. Yeah, question. So if you are one of the things I like to say is that to do science, it's okay to make approximations, right? It helps us make progress. It's not okay or to make assumptions, make approximations and make assumptions. I'm going to assume that this is a small angle limit. I'm going to assume that this regulatory pathway is negligible, right, or second order. It's okay to make those assumptions to help us make progress in understanding. It's not okay to forget what assumptions you've made, right? And so you just have to keep in mind that this is only true, exactly true, if you go back far enough from the screen. How far back? It has to be large compared to the opening between the slits, the gap between the slits, right? If you really looked in the near field, right, and you only look like 2 microns, 3 microns away from these openings, then this relationship would not hold exactly anymore. Okay? Does that answer your question? Okay. So it makes, I think at this point, most of you can intuit that if I wanted to ask for where do I see complete destructive interference, where are I going to cancel, that I need that path length now to be either 1/2 wavelength different, or 1.5, or 2.5, or 3.5. And just writing that out in mathematical form. And for this formula and the previous formula, we start with m equal to 0, right? Because for this one, we wanted to make sure to count the central maximum, right? And the central maximum is at an angle of 0, right? That central one. So by allowing m to be 0, we get an angle of 0 as being one of the solutions, right? And then the first one is m equal to 1, first bright fringe off axis, right? So keeping with that notation, if m's allowed to be 0, then the first bright fringe is going to be when this delta is 1/2 wavelength. So we just stick an m plus 1/2 in here. Next one would be at m equal to 1, which would give us 1.5, and so on and so on. Right, and again, you can see how we're starting to pile up equations, just like last quarter, right? Lots of equations, lots of very similar equations, and you can memorize them for a short time, and then the next time you study for an OChem test, the teacup floweth over and things fall out, but it doesn't take much to derive it, right? You can think things have to be small, you make the picture of, they have to be a wavelength apart, right? And you look at those equations and you say, in this case, which one of these equations will get me having the path length difference be a wavelength apart, right? And so if you forget, you can reason it out very quickly. All right, so angles is one thing, but we don't typically like to sit there and take protractors and try and measure angles. What we want to do is shine this light or this interference pattern, right, onto a piece of film, or in these days it would be a CCD camera, right? And I want to say, where on my CCD camera, where am I on my CCD chip, am I going to see the bright fringe, right? So we have a flat panel here, and we want to know how far out along this detector array, which could be my eye, it could be my retina, it could be a CCD chip, am I actually going to see the center of that bright fringe, right? And then here, what we're going to do is, like I said, if we really do have these things very, very far away, and we have reasonably, for most of these experiments that we do, we have diffraction at small angles. And again, for this equation, we're making the assumption of small angles, and you have to remember that, right? You can get diffraction at large angles, and we might have to deal with that. And then I have to tell you whether the angles I'm talking about are in the small angle limit or not. And if it's on a quiz and you don't know, you can ask me. Okay? Right. Typically, less than 10 degrees counts, but I wouldn't expect you to have to make that judgment call. Right. So if the angles are small, because again, we've exaggerated this to make it fit on a slide, right? Then the sine of the angle is approximately equal to the angle. So is the tangent of the angle. So we're just going to treat all of these things as the same. Right. So we already have the angle. We know how to calculate that angle. If I want to know where it is on the screen, that's just trigonometry, right? Tangent of this angle is going to be the opposite over the adjacent. The opposite is this delta y, how far that peak was going to show up on the camera plane. The adjacent is just how the distance between my two slits and my camera, or my film plane, right, or my screen, or whatever I've been calling it. Right, so y over L is going to be the tangent of the angle. Right? But if you look back at our equation, we don't have the tangent of the angle. We have the sine of the angle. Right? So unless I want to if I want to do this exactly, I would have to calculate the angle, by taking the arc sine from this equation, right, reversing that, and then taking the tangent of that, right, and that would give me the exact answer, but that's a lot of work, right? So if I just pretend that the sine and the angle and the tangent of the angle are practically the same, then I can substitute the tangent for the sine, and I get y is just equal to L sine theta. Okay? And in that case, you can then substitute that back into the sine angle, the sine theta that we just calculated, right, and get our interference pattern based on these equations. All right, so let's let me see what. Trying to do this so quickly that you can't see what the solutions are. Yeah. Okay. You probably saw the solution at this point. Let's just work through it, but I'm not going to do this for credit. Let's take a few minutes to work this through. We already had 2 clickers. There's no point. I know some people already had to leave, but I don't want to jump into the next topic. So let's work through this. Make sure we know how to do the math, and we'll work the answer on the board, and then we'll call it for the day. So we have light shining on this double slit interference apparatus. It has this frequency, 6 times 10 to the 14 hertz, right? Oh, one thing I think I haven't put up on slides yet. Speed of light in air or vacuum is given the symbol c, and that's equal to 3 times 10 to the 8 meters per second. I think that would have been in a slide from the chapter we jumped over. I forgot, didn't catch that. Great. So at a point P on the slide, on the screen, the first bright fringe appears. I want you to tell me what the path length difference between these paths has to be. So this is a good example of making sure you just kind of read the question, think about what it's asking. Don't just immediately jump into, because we now have like 5 formulas we could use, right? But don't jump into a formula and assume that I have to start plugging stuff in. Right? Just think about what it's asking first. So I want to interrupt for a moment. If I don't get to the solution, you guys can work it out at home. I can post it and we can go over it next time if you want. But I want to make sure people kind of have an intuition for this result, right? So what this says is if I take those 2 slits, right? Remember D was the separation between the slits, and we worked this all out basically with a little bit of math and a lot of intuition, right? But in the end, we have something where we say, if for a particular wave coming in, if I make the slits closer together, make this smaller, right? Those bright fringes will move further apart, right? I want you to get an intuition for that, right? Because if you start getting an intuition for these things, it really does help, right? Why is it that putting the slits closer together causes the place where the 2 waves line up, 1 wavelength apart, end up being further apart now? All right, I will post the solution in the slides, and then if anybody has a question, we can go over it first thing on Friday. Thank you, guys.